I'm going to teach you guys about what's called the hype cycle. Now, the hype cycle is something that they came up with a while ago. I'm not actually sure who came up with it, but it's pretty much the idea that applies to all new technologies, right? So the idea is there's some sort of trigger that causes the development of a technology, right? And then everyone gets super, super excited about the technology. There's a flood of information and research. Everyone is getting like super into it. They think it's going to totally revolutionize the world, and it gets up to here, all right? So on this axis you have visibility, and on this axis you have time. So the longer that the technology is out there in the world, the more it's progressing along here. And to get from about here to about here is in the range of 10 to 15 years for most technologies, okay? The idea with the visibility is how promoted is the technology in culture, in society in general, right? So once you have the technology trigger and the technology hits the market, all of a sudden it ends up all the way up here. It's the must-have thing. This is like, you know, they release a new gaming system right before Christmas, and it's like, bam, everyone needs it. Everyone wants to do cool things with it, right? So you're at the peak of inflated expectations. The idea here is that this is the most pervasive the technology will ever actually be, because people at this stage are coming up with applications for the technology that are kind of beyond what the technology can actually do. And they're trying to apply it to areas that maybe it's capable of being applied to, but it's not really economically feasible, so it'll never really end up in that kind of a route. But the thing is, you see how it drops off down here, because when you're at the peak of inflated expectations, people are coming up with ideas on how to use technology. Even if it's an idea that will become technologically feasible, it's not quite feasible at this moment, right? So people are going to come up with a lot more ideas than you're actually capable of implementing with the technology in its more like infantile stage, right? So then what happens is all these people fall off the technology bandwagon, and you end up in the trough of disillusionment. It sounds like a J.R.R. Tolkien book here. So you're in the trough of disillusionment, and at this point, people are like really disappointed because they're like, oh, this is a cool technology, but we can't really use it, and maybe it doesn't really apply to as many areas as we thought. Maybe it's just not as great as we thought it would be. And then what starts to happen is people actually, as time passes, people develop associated technologies that allow you to use this new tool, right? And people start figuring out that, hey, actually we can apply it here. And we can definitely apply it here. So we create a little bit of a program, and this is kind of where a lot of the technology that you guys are learning about in this class are in these kinds of areas, right? So you have new technologies that are coming in, things like a lot of people would put like blockchain up here, these kinds of like new ideas that are just hitting, they're like the buzzwords, and then you fall into the trough of disillusionment, and slowly but surely people start applying the technology, and you end up the slope of enlightenment onto the plateau of productivity. And the plateau of productivity is it. This is it. This is where the technology is going to be in culture. Things that are there are things like Microsoft Excel, right? Everyone knows how to use it. It's totally permeated into the society, and there's not much more that you could do with it that isn't being done with it right now, right? So this is the end area where technologies all end up. And as I mentioned at the beginning, to get from here to there is usually like 10 to 15 years. But obviously for some technologies that takes a lot longer. For other technologies, it's a lot quicker, right? We're gonna talk about artificial intelligence, and applying this to artificial intelligence, you really can see a lot of cool things, right? Because originally when AI first came out, and you're coming up here to the peak of inflated expectations, everyone predicted, all right, in 10 years' time, machines are going to be doing all these cool things. And then slowly people started to realize, right, like it's a lot harder to program these rules into a computer and make the computer execute the way that you want it to. So then you fall into the trough of disillusionment. And in terms of artificial intelligence, when you look at something like expert systems, this actually caused effectively like a recession in Silicon Valley, because a lot of startups back in the 80s invested heavily in expert systems, and it all kind of just died out. And when the trough of disillusionment hit with expert systems, companies went bankrupt, right? And then slowly but surely, other people, academics, researchers, they realize like, hang on, there might actually be something here with expert systems. So slowly they start implementing those, and then you get to somewhere like here where we are now, where we're not at the plateau of productivity because it's not totally permeated into society yet, it's not fully mature, but it's on its way there, right? So something like AI, where people originally predicted that it would be like 10 or 15 years, they're now saying like, oh, in 40 years time, we'll have machines doing things, right? So this timeline is flexible, but 10 to 15 years, that's usually what we say for most technologies, right? Because most things like text messaging or something like that, it's not a very complicated technology to develop, so it moves through kind of quickly. Any questions on the hype cycle? You guys getting hyped to learn about this? So pretty much this is what I went over. It describes the evolution. It takes about 10 to 15 years. The trigger is what initially causes it. So that's, in the case of blockchain, the Satoshi Nakamoto paper that I talked about, where they first published it. Or for most people, it was like the idea of trading in Bitcoin was what kind of led the idea of blockchain in their minds. Then when you reach the maximum hype, that's when it gets the most visibility, because now, like, okay, yeah, blockchain is a bit of a buzzword or whatever, maybe it's not as full on in the cycle, but when you get to the later stages, your average person doesn't really care about it. It's just people that are applying the technology that care about it. That's why we have the little difference of visibility between those two. Yeah, it's limited by technological implementation aspects, and then when technology catches up, you end up on the plateau. Right? So let's switch gears back to AI for a little bit and talk a little bit about the origins of AI. This is kind of a complicated topic. It's going to turn into a little bit of a history lesson, and I apologize for that, but it's really, really important to learn about where it came from, to learn about where it's going to go, all right? So first discussion of artificial intelligence was in Greek mythology, and they kind of came up with this idea that in the future there'll be some sort of machine, right, before like the idea of a machine was totally formalized, that would be a servant to humans, and that would be able to do things for us. It kind of overlaps with a robot, but the difference is that like robots can exhibit forms of artificial intelligence, right? But you can also just have robots that you control, right? And the idea behind artificial intelligence is that it's a machine that can kind of think for itself almost, right? So just an aside, I think I have a slide coming up later, but I think I should tell you guys this like now, right? So currently there are 3 classifications for artificial intelligence, right? There's weak AI, which is the simplest form of artificial intelligence. And that is when you totally program rules into the machine, and the machine executes based on the rules. So the machine isn't really thinking too much about what it's doing, it's just executing based on what you're telling it to do, right? Then you have the level of artificial intelligence that a majority of our advanced systems operate on right now, which is moderate AI. That is something like Watson. So a moderate AI system is able to deduce and come up with its own sets of rules, but it's not totally self-functioning. It still needs humans to input the rules in the first place, give it guidelines on how to come up with new kinds of rules, and how to operate effectively. And then the final version of AI is strong AI, which is something that doesn't exist. This is up for debate because some people believe that it kind of exists. But strong AI is AI that is totally able to it's like self-aware almost. It can function totally on its own. And the real key with strong AI is it's able to write its own code, right? So if it sees a problem it can't solve, it's able to draw on other knowledge and come up with its own solutions. And the other final portion of it is something we're going to talk about in a few minutes, is that strong AI is able to pass the Turing test, right? And the Turing test, for those of you who don't know, is basically this idea that was come up with by this famous mathematician that we're going to go into detail about. And he pretty much said that a computer can be classified as being artificially intelligent if a human being that is interacting with the computer is unaware as to whether or not it's interacting with a computer or a human. So the idea is the computer can actually fool a human into thinking that it's interacting with another human and not a computer. But so there are machines that are able to pass that test, but we don't consider them being strong AI. Yeah.
Do we need quantum mechanics to get to that level?
No, I don't think so. Because you just need to be able to come up with a machine that has a strong enough set of rules that it can always self-execute to solve the problems. The problem is coming up with that set of rules in the first place. And there's too many issues. So with the Turing test, there are machines that have passed it, right? We've had machines that can technically pass a Turing test for a long time now, since like the 80s, right? And a lot of the times, like a great example is like a lot of times you'll be online, right? And if you're on like the Verizon website, for instance, when they detect that you're there, they open up a chat window and you're talking to someone on the chat. But a lot of times you're not actually talking to someone. But a lot of people would assume that it's a person on the other side because of the way the computer communicates. But those are mostly just like they're fooling a human, right? So it is passing the test, but the essence of the test in most computer science theory is the idea that it is smart enough to fool a human. But in these cases, you're just programming it to fool a human, right? And that's not very difficult to do for most people, right? So that's why the idea of strong AI being a thing that actually exists is kind of up for debate, right? Because Watson, for instance, they can search the internet and come up with solutions to problems that it's not directly programmed to come up with the solution, right? It's not programmed to know every possible answer to a multiplication table. But the idea is, people argue it's not strong AI because it's not writing the program that tells it to go look for that information. That is being written by a human and being programmed into Watson. So Watson knows if I don't have this data available to me, this is the procedure I have to go through to get it, right? It's not coming up with that procedure on its own. It's just weighting the procedure differently based on the iterations of the operation. Does that answer your question? All right, so it was first discussed back in Greek mythology. Then in the 1600s, this is like all way before computers, right? They came up with this idea that machines could be used to solve logic equations. Logic equations is like very basic, like if-then kind of statements. And the idea was that logic can be made simple enough in a common enough language that you could maybe someday invent a machine that's able to process these algorithms and give you answers based on what you're trying to solve, right? So you can see that this all starts off very simple and very logically. So then in the 20th century, the birth of computing allows us to become possible with the invention of computers, which we're going to go into in a minute. And now AI, or artificial intelligence, is totally integrated into our life. Like, if you have an iPhone or a MacBook, you have Siri, and that's AI, right? It's able to search the system for potential questions or answers to your questions. Even the idea that it's able to process the language that you're giving it and come up with what question you're actually asking it is an example of artificial intelligence. But we'll go into the classifications of AI in a minute. So this is really the birth of computing and the birth of AI. And this guy, Alan Turing, if you guys have some free time and you're on Netflix or you have access to it, I would highly recommend that you go out and watch the movie The Imitation Game. This is all about this and how he came up with all of this. But basically, he was this British mathematician, right? And there's like other social issues that's going on with him. He had like other issues, but basically we're going to talk about him in a professional sense here. And he became totally fascinated by machinery, right? And in 1928, this guy, David Hilbert, came up with this thing, right? Einstein's problem, right? You don't really have to know it, it's German, right? But that was back when German was the main language of science. So it basically translates to decision problem, right? And he posed this question to mathematicians. It was a whole host of questions, but this was what ended up becoming one of the more famous ones. And his idea was, is there such a way, right, that you could come up with an algorithm to determine that any statement is universally true or not, right? Because we have this big problem in science where people come up with theories. You can't prove that a theory is right 100% of the time because you can't possibly run all the different iterations. So this became like a huge deal. Like, can you actually come up with some sort of system of testing theories to prove that they're not theories, they're actually facts, that they're right 100% of the time or not. And if they're not right, can you come up with an instance where it's for sure wrong, right? So he posed this question, and the greatest mathematical minds in the world went hard to work to try to solve this. And Turing actually ended up solving it. He took a roundabout method of doing it. He solved it the same time as another guy, I believe his last name was Clark. They published their papers like 4 months apart. But the interesting thing is they took two totally different approaches to solving this problem, and they both came up with the same answer, right? And Turing's answer is considered a little bit more robust because it's a more formal response, but they got joint credit for it, right? So he was fascinated by this, and his knowledge of machinery is really what led him to solving this, right? So he began working on this idea that you could use a machine to solve a logical algorithm. That was the first step to his problem. Because eventually what he was going to do was that he was going to prove that if you have a machine that can solve algorithm problems, then if this was true, if you can actually determine if a statement is universally true or not, then you can predict the actions of the machine 100% of the time and know exactly where the machine is going to be in the process at all times, right? And he found out through his work later on that that's not possible to do, and therefore you can't actually prove that a logical statement is universally true or not. Always, right? So while he's working on this, World War II breaks out. And this is actually really, really important because without World War II, there's a lot of stuff that we wouldn't have, and maybe we would have the kind of technology that he came up with, but not to the degree, right? Not in the same kind of depth, right? So this seems kind of an aside, but it's all going to loop back up. And the Nazis, they came up with this machine called the Enigma machine. For those of you that don't know, this machine was like a super advanced communication system that allowed the Germans to communicate with each other on open radio channels with no worry about Allied interception because their encryption scheme using the Enigma machine was so complicated that the Allies couldn't figure it out, right? And it was bad. I mean, literally, like they would be like torpedoing the supply vessels that were going to the UK at the time, and they would hear the calls on the radio, but they wouldn't be able to have any idea where the different submarines were actually going because they really couldn't decipher this. So the way that this works, this machine, right? Because this is really important to how this all comes back together, is that it's a set of rotors and alphabets. All right, you know what? I could go through this, but I'm just going to show you the picture. It's a lot simpler. This is what an Enigma machine looks like, right? This is what they would have on board each individual boat or whatever they were operating. And when you close this top down, this is like the inside, you would see the rotors here, you would see the numbers on the rotors, you would see these little light bulbs in there lighting up behind letters, and then you would have access to this keyboard and this plug board here. So what happens is you set up the system and you type your message as it would read in English or German or whatever language you want to type it. And the system would operate, which I'm going to show you in a minute, and output would be a random letter. And what would happen is these bulbs would each correspond to a different letter, and the letter that would be output, the bulb would turn on, and that would be the letter that you would see, and it would be recorded into the system as that letter. So if you hit A, then D might light up. The ingenious part of the Enigma system is these rotors, right? And these rotors actually rotate with each time you type a letter. So if you type A and then you type A again, it might show up as D the first time, but the second time it could show up as a completely different letter. So theoretically, each individual letter in a note operates on its own cryptographic scheme. So to do traditional cryptography on it, like what you do with traditional cryptography is you try to look for common letters in the entire message, and you try to break the scheme that way, and once you've figured out one or two common words, then you know, like T is represented by an X. So any X in the entire message is a T, right? That's the simplest way of doing it. But this totally nullifies that as an option. And the way that it works is like this, right? So you want to type the letter A. So you hit the connector for A, this is like a little key, right? And the wiring goes through to the bottom of the plug board. So what the plug board does is it randomly switches letters in the first place. So you get one level of switching. So in this particular plug board configuration for today, so every day they would reset their rotors and their plug boards based on a chart, right? Even if the allies got a hold of the chart, it wouldn't make a difference because they don't have access to the internal workings of the Enigma machines to know what those settings actually mean, right? So some of the letters get switched, but some of them don't on the plug board. So in this case, A doesn't get switched. So A stays the same here. Then it goes up to the rotors, right? And you set the numbers. So in this case, your rotors might be like 6, 5, 5, 5, 4, right? Or whatever. So you set the rotors. So the number goes up here, and it gets switched within the rotor. So it's down here, it gets switched up there, it gets switched into the middle, it gets switched back, and then it does the whole process again in reverse. And then you end up coming out through this second node right here, right? Because that's where it happens to be. Comes in through, back down to the switchboard. In this case, it enters at the letter S. The S and D are switched on the plug board, so it goes through the plug up to D, and the letter D lights up, right? While it goes through the rotors and back, the rotors shift one movement in either direction. And when that happens, the next time you type A and it gets to the rotors, say it's shifted downwards. So instead of entering at this node, you're now entering at this node. So instead of switching all the way to the top, you're now switching elsewhere. So you see how this all gets switched up, and you may actually come out this time, say maybe you come out on the third node from the top because all the rotors have gotten shuffled. Well, guess what? Now you're coming out of D. D and S are switched, so you're coming out of S. Or you could be coming out of F, and F remains F. Right? So you can see how this becomes super complicated. All right. That's enough about Enigma. But basically, the idea here is they were totally stumped. So the British founded this thing called Bletchley Park, where they got the top mathematicians and cryptologists in the world to get together to try to break this system. They had no idea this was the system, but they knew that they had to break this so that they could figure out what was actually going on, right? And most of the scientists came up with like different cryptographic schemes by like doing letter switching, still thinking that it's like a regular table or something like that. But this guy, Alan Turing, was like, no, I have a way better idea. There's no way that we can crack the algorithm that is producing these letters. He didn't know how it actually operated, but he did know that there was no way he could crack the algorithm. So he said, instead of trying to crack the algorithm by looking for the algorithm, why don't we just do it regularly, right? If you had a short letter and you didn't really know anything about cryptography, one way that you could try to solve it is by brute force. You could just plug in letter after letter after letter until you get a message that is readable in English, right? And everyone thought that he was absolutely crazy. Like, there's no way, because a team of 100 people could be looking at the same Enigma message for weeks and weeks and months and not be able to brute force break it, right? So how are you going to do that? And so his idea was to come up with a machine that does it. So he invented the automatic computing engine, which he didn't get credit for a while afterwards because it was top secret. And basically what this is this, the world's first computer. It was very loud, very noisy, very, very big, right? And pretty much what it does is each of these different disks houses a bunch of smaller disks, and pretty much what they're doing is each bank is brute force trying to say, all right, try, you have a 3-letter word, try AAA, AAB, AAC, right? And you start them all at random start points that are separated, and the hope is that if you do this enough times, like the number of computing power that this is like hundreds of thousands of people. So the idea is if you have hundreds of thousands of people that are operating together to try to do this, hopefully in a short enough amount of time, you'll be able to crack what the message reads in plain English and be able to decipher it. And he was able to do it. Yeah, people thought he was crazy. And the first message took him a long time to decipher. But it ended up working. And for a long time, the British were able to understand what the Germans were saying, but they didn't want the Germans to know. So they were actually picking and choosing what information they were going to act on. And nobody knew about this. The Americans didn't know anything. So yeah, he used the first order logic to do this, pretty much the brute force method, and it said, told the machine like if this is a readable word, stop. If not, continue. And it was just basically a big tokenized decision tree with rotors in it. But yeah, no, it was the world's first computer. He did it, right? So after World War II, he uses this to prove the fact that you can't actually know if an algorithm is universally true or not, because he said, like, look, I have this giant machine, right, that can compute any kind of algorithm, and I can compute like a tremendous number of iterations or anything like that. But theoretically, even if I use my brute force machine here to calculate every single iteration and come up with the fact that, no, 100% of the time there's going to be a correct answer, then I should be able to predict a window of time that my machine should be able to stop in, right? Because there's a finite number of iterations. You can't have an infinite number. And he proved that that's actually not true, and you can't predict when it's going to come to an end, because there are actually infinite iterations and different things that you can't handle in every algorithm. So that's what he used his first computer for. This is also the birth of AI, because he starts to consider what actually happens when he runs these computers. How advanced can these computers become? And he ends up formalizing in the 1950s this idea of artificial intelligence with the Turing test. The idea that, can you create a machine that is capable of fooling humans? The original Turing test was set up as follows. You have a person sitting at a desk. The person sitting at the desk is talking into a computer. Well, not talking, typing into a computer, right? And you have two situations connecting to that computer. On one side, you have a human, and on one side, you have nothing, just a machine, right? And some of the questions are going to be answered by the human, and some of the questions are going to be answered by the machine. And if this person can't tell who's answering which questions, your machine has passed the Turing test, right? But obviously, things have gotten a little more complicated since then. So the Turing test has kind of evolved, but that was his original idea for it. So that was sort of the beginning of the conversation on artificial intelligence in academia beyond what they mentioned in the 1600s. The idea that you could use machines to kind of fool humans and to do different human types of tasks. Then in 1964, this guy Dreyfus, he formally classified AI into four main areas, right? There's game playing, problem solving, language translation, and pattern recognition, right? So for game playing, we now have computers that can beat chess masters. You have Watson that can beat Jeopardy players. So this is just the idea that you program in a set of rules, and the machine is able to manipulate those rules to come up with a common goal of winning a game, right? So the idea of chess is you know the rules for what winning is, what losing is, and how pieces can move around the board. Can you program a machine that can actually understand, okay, what it means when the pieces move into different places with respect to getting to the end goal of winning the game? For problem solving, it's a similar thing, but it's a little simpler. The idea is that you come up with a problem. So the machine has learned all different solutions to the problem. So can the machine determine the correct solution for solving the problem? Or does the machine know where to access the solution data? So both of these are kind of ideas that have bled through into the modern application for AI, especially in the respect of accounting and auditing and things like that. The next area is language translation. This was the most challenging. And to be honest with you, in terms of all the AI areas that exist, this is the original four areas. They change it. But this is the one that we have the most trouble with. There's so many languages out there, and understanding different dialects, different patterns of speech is very, very difficult. I mean, we live in an era where there's things like Google Translate. Even Google Translate gets it wrong sometimes. Even Siri doesn't understand you sometimes. The important thing with these language softwares is that they only learn by doing. So the more that they are used, the better they become, right? That's why my professor, he's got like a Hungarian accent, right? Siri couldn't understand him. Like when Siri first got out on his phone, it was actually pretty comical. Like could not understand it at all. But now Siri actually kind of understands it. Does a much better job. And that only comes with time. not only from him putting into Siri and Siri understanding him personally on his phone's level, but also Siri collecting the data from all the people with a Hungarian accent and all the people that are using this kind of dialect and putting things out there. Interesting thing for language translation is now there's a movement by Google and some other big players to develop a universal computer language. I mean, there are computer languages, but what they want to try to do is come up with a universal language so that when you translate, you see, if you have 3 languages, right? You have English, French, and Spanish, right? I mean, yes, they're similar. And you want to use Google Translate so that you can allow the translation between these different languages, right? So if you have English, French, and Spanish here, you need one program that translates English to French. You need a separate set of rules that translates English to Spanish. You need a whole separate set of rules that does French back to English, because the words aren't always in the same order, right? And you can have different turns of phrase. You then need a separate program that does French into Spanish. You then need another 2 programs for Spanish into English and Spanish into French. So here you have 2, 4, 6, right? That's just for 3 languages. You need 6 separate algorithms to do that. Now you can imagine that, like, for example, South Africa has 23 official languages, right? So you multiply that out and it's a tremendous number of programs that you need to do. The idea is, instead of doing this, if I enter in a machine language in the middle, then all I need is English to machine, French to machine, Spanish to machine. So that's only 3. And because it's the machine language and you can program it however you want, you don't even need to come up with a separate set of rules to go machine to English or something like that, because guess what? I mean, even if you do, right? So say you need to come up with English machine to French, machine to Spanish. When you add a new language into this equation, like let's add in Portuguese, right? Instead of having to do Portuguese to English, Portuguese to French, Portuguese to Spanish, you only need to come up with 2, Portuguese to machine and machine to Portuguese. So adding languages into the database becomes way, way simpler. So that's what they're trying to do here. Then for pattern recognition, we're going to go into more detail about this later today, but basically this is how you can not only recognize patterns in terms of data patterns, but more importantly, this is what leads into the ability to determine facial recognitions and things like that. Okay? Yeah?
Isn't XML or XBRL kind of like that?
Yeah. It's sort of like this. It's machine readable, but it's not designed to be. Used for like translating into languages and things like that. It's just designed to be displaying characters and different sets of data on the screen. All right. So he came up with these 4 areas in 1964. This was the original areas of AI. Then, in the same year, this dude McCarthy, he established the Stanford Artificial Intelligence Lab, right? And he told the people at the Pentagon, in the next 10 years, we'll have an AI machine for you guys that can operate and do all these kind of crazy things in all those 4 areas. 20 years later, damn, they were still waiting, you know? And obviously the Pentagon wasn't so happy, right? And all of a sudden, all of these different firms that were trying to push AI, like they fell into the trough of disillusionment. And this is what I was talking about, the winter of AI, the recession that hit Silicon Valley. And it caused a lot of firms to go under because many people had invested very heavily in this idea that AI was going to come around quick. They started developing peripheral types of applications. They pretty much put the cart before the horse, right? And they were left out in the cold, so to speak. And winter came, and winter removed a lot of those firms. But you know what? Silicon Valley's back, and it's better than ever. So in the 1960s, also, one of the Stanford professors named Freiman, he came up with this idea that instead of following logical software patterns, right? Because the idea originally was to do that, use some software patterns. You can actually get a machine to emulate what a human expertise would be. And this is really important for us because this is the birth of expert systems, right? Expert systems later becomes the 5th area of artificial intelligence, right? The idea behind expert systems, we're going to go into a little more detail, but the idea here is you program it with expert knowledge and then it can act as an expert, so you don't always need an expert on the side. So then came the 1990s, and artificial intelligence had expanded to these 5 areas. And this is the current 5 areas of artificial intelligence that you guys need. Natural languages, that's pretty much the same as what we spoke about before, but the difference is, in the original idea with the language, it was just translational. Here it's also the ability to understand what people are saying, to pick up on nuances so that you don't have to type things in a formal set of English. You can free-form type a response, and the machine can still understand what you're trying to say. Expert systems, which is the idea that you program a system to act like an expert so that you don't need an expert on hand. So for an auditing standpoint, all of a sudden you don't need a tax expert with you if you're auditing a section that pertains to tax. You can have an expert system that can do the exact same work without you having to pay the professional to be on site. Cognition and learning, which is the ability for machines to adapt. It kind of overlaps to a few of the areas that we discussed before. Basically, this is where you get your Watsons and things like that are able to adapt to their environments. The next one is computer vision. That's as simple as it sounds. Computers are able to see and interact with the world. That comes with the pattern recognition ideas. And then automatic deduction. This is the idea that they can solve problems without being programmed with a specific set of rules necessarily, right? That they're able to adapt and overcome any potential obstacles and solve problems, right? So with respect to Watson, a lot of people thought there was no way that it could win on a game like Jeopardy, because yes, they have the ability to search the internet, but it may not have the ability to understand particular turns of phrase or the unique wording that occurs in a lot of Jeopardy questions. But obviously, because of its natural language capabilities, Watson was able to defeat that, and it absolutely blew all the contestants away on Jeopardy. So, in the 1990s, the most prolific discussion on AI seemed to center around expert systems. This is what we're talking about now. We're going to go over a lot of different things today, but expert systems is going to be a major one of those. The discussion has sort of died down, right? So if you remember the hype curve, the 90s, it was probably like up here. Then in the 2000s, you kind of fell into the trough, but we're actually going up the slope of enlightenment right now towards the plateau. So people are researching about it. It's much slower than it used to be. People are looking at applications, and people are actually creating accounting applications for this. But it's nowhere near what they thought it was going to be, right? Because it never is. That's what she said. So that's the movement of AI. So basically, what it's defined as is the simulation of human intelligence, and it's processed by machines. AI is used in all of these areas and more. Like I said, everyone has, well, not everyone, I don't have it at least. If you have like the Amazon Dot or Echo, right, then you have an AI system in your house, right? You can search the internet and tell you all different kinds of pieces of information. Siri, they use it for stock trading, they use it for predictive trading. I don't know if you guys remember, but when we were talking about the candlesticks, I was telling you guys, like, yeah, they program in all these different types of parameters, and the computer effectively does the trading on its own. They use it for diagnoses. If you use WebMD to try to figure out what's wrong with you, that's technically an expert system, and it's artificial intelligence, right? Because they program it with all the doctor's knowledge, and it's sort of diagnosing, right, within a realm of accuracy. They use it in auditing, like I mentioned before. One great example of this is the fact that they're developing audit dashboards. So when you just plug in the information and you're getting ready for your planning stage of the audit dashboard will usually be able to tell you exactly what kind of tests you should run, what an accurate materiality threshold would likely be, all these kinds of things. So they use it in auditing. Weather simulations, the very fact that we have like weather updates and things like that, like, okay, the radar exists and the predictive modeling exists, but now when you plug it in to a machine learning algorithm that can predict over and over and over again, this is what happens when this happens, they're using it to simulate weather data. And that's why some countries have more accurate data than others, because they invest in this. And then drones, right? We have like drones in the military, and like, yeah, okay, there's a guy that operates the drones. most of the time, but not all of the time. And they have drones that go into disaster sites and they sniff out problems like people that are trapped. Or they're using drones right now, actually they're using AI drones at Fukushima. For those of you that don't know, there was a big tsunami that took out Japan and absolutely wrecked one of their nuclear power plants. And it's been leaking radioactive water for a while, and people are trying to solve this problem. So they have drones that they're going in to try to inspect it. And they have drones that are operating around the plant with radiation detectors that are operating autonomously, and they're reporting back if there's any abnormal spikes or areas of high-risk radiation that could potentially spread out into the surrounding environment. So that's kind of some areas where AI is used these days. There's many, many more, I'm sure you can think of it. AI obviously is like a big thing in pop culture, right? It's in a lot of movies. If you've seen The Matrix or The Terminator or Blade Runner or like so many other movies. Space Odyssey, 2001: A Space Odyssey, that's another good one, HAL. So yeah, pretty much it's a big deal, like people know about it, but we're hopefully gonna teach you guys today exactly what it is. So the big thing here is, can we or do we trust artificial intelligence, right? Obviously, it's only as good as the rules that you can program in. We don't have any strong AI that's capable of writing its own code yet. And as a result, we can only trust it insofar as we know that the data being supplied into the system is good. The rules within the system are good rules. There's no holes in those rules or those logic systems. And even once we get to a stage where there's strong AI, like look at these movies here, right? Like everyone's seen The Matrix, right? Machines take over the world, and humans are being mined for their battery potential, right? And like, do we really want an AI that can effectively self-replicate, that can write its own code, create its own nodes on a network, and operate almost like a human, right? I mean, artificial intelligence, that's the whole point. That's what people are working towards. Is that something that we actually want? Now, a lot of times, like, people don't consider this when they talk about technology, because guess what? It doesn't really matter. I mean, granted, there are impacts with everyone having a cell phone, right? We're seeing some of those impacts. Like, you come to class, people are all out on their cell phones. Like, here, you're all on your laptops, right? Like, I don't mind, but like, it is what it is. There are impacts that are real. But the huge negatives, like, are way outweighed by the positives. But when you talk about something like artificial intelligence, I don't know that we can necessarily determine what those negatives are, right? We may not be able to comprehend what it would be like to have a machine that can do this, that could outthink us effectively, right? I mean, Watson can beat people in Jeopardy. Who's to say that you can't develop a Watson that can operate like military technology with ease and mess up the other kinds of computer systems that we operate out there, right? And while there are a lot of unintended consequences with technologies, fortunately, most of the technology is not disruptive enough that it can cause major unintended consequences with great negative side effects. But this could, right? And this is a debate, right? My professor, he loves the idea of artificial intelligence. He thinks I'm crazy. He thinks that it would be wonderful to live in a world where machines do everything and humans can just sit back and relax. And how bad could the consequences really be when the rewards is not having to do anything? But it's a debate, right? I mean, everyone's entitled to their opinion. So that's something that we consider. And when you are implementing this into an auditing setting, there are also consequences, right? I mean, there are people that can be put out of jobs. Now, I know people that work in the industry that implement technology into businesses, and they are 100% adamant that I was talking to him literally yesterday about this, and he said, I've gone to so many companies and implemented technologies, and he does this in the tax realm, right? So he makes it so that people don't have to worry about doing taxes for the company. But he swears up and down that he has never had a person at any of the companies he's ever consulted at lose their job, not even one, right? And he says that the real benefit here, which I can believe, is that when you implement these technologies, you're freeing up the person's time to do other more complicated tasks that the machine can't do. The worry here with AI is that maybe the machine can do every task, and then what do you do, all right? How do you distribute resources in the economy, all that kind of stuff? All right, questions on the background stuff on AI? All right, what do we have next? AI and auditing? Yeah, we'll do this slide, why All right, so there's two main areas of concern. So you have auditing intelligent systems. So how do you actually audit an AI system, especially if an AI system is worth a huge amount of money to a company? How do you account for that value? How do you account for any potential problems that the machine could experience? This is especially difficult because most auditors don't have any technical training in these kinds of areas, so they don't actually know what kind of problems that this could bring, right? One step further, if you have an intelligent system that's actually doing accounting work within the company, how do you audit that to make sure that it's performing its job correctly and there's no material misstatements or anything like that? On the flip side, how can you use intelligent systems as an auditing tool to make sure that you do a better audit? So auditors, they're kind of reluctant to do this because they're very worried that if they implement mechanical systems to do jobs, that the machine might not operate effectively and they're going to be the ones that get sued when the company goes under, right? This whole litigation problem that we've spoken about before, right? The auditor is still in business, the company's out of business, who are they going to come sue? The auditor. So the auditors are concerned that the system that they're using isn't working properly, but they are still using some level of intelligent systems in some manner. Like, you've learned all about the different types of tools and programs that they use. A lot of these can be considered intelligent systems. The ones we're going to learn about today are definitely intelligent systems because, by definition, they are. It's artificial intelligence. So yeah, there's that. Obviously, we know that these systems aren't prevalent. They're not everyday life. Like, people still pay millions and millions of dollars just to get time on Watson, right? And the big reason why this is the case is not because there's a lack of applications in auditing, but there's a reluctancy and there's a rule. I'm blanking on the number, I think it's 305, but there's a rule. And it specifically prevents auditors from using data from a previous audit for another company on a current audit, right? And that's how it's written, right? You can't use data, you can't use a client's data when performing an audit on a separate client. You can, however, in the rule, use your experience, right? So what's the difference? I don't really know, but you can use your experience gained, but you can't use the actual data, all right? So the problem is, to run a majority of these artificial intelligence machines, you need a huge amount of programming data to go in, training data, that's what they call it, right? Because the system is only as good as it's performed in the past. So the idea is, if you have some sort of system and you put in a bunch of input and you get a whole bunch of output, right? You want to train the system to do this output procedure as well as possible, right? So how do you do that? You start by giving the system a whole bunch of information that you already know the output for. So you use past information that's occurred. You use past, if you're doing auditing, you use past year sales and past year's gross income or whatever. Like, say you're using purchases to predict sales, right? So you're using past year's sales, past year's past year's purchases, past year's sales. You know the sales, right? So the machine can run and say, all right, based on all this data that I've been given and all the results, this is the best possible combination of algorithms that I can use to get this result, right? So that when you put in some sort of X and you have no idea what the outcome is going to be, then you have a lot of faith that the machine has done the same process enough times and gotten the correct result enough times that this time your result's going to be pretty close. But in order to do this, to get a machine that can do this very well, requires like millions and millions and millions and millions of records, right? So the problem with it in an auditing context is it actually acceptable under that rule for you to input client data from other audits as training data and use the current year audit for your current client as the unknown data? And technically what the lawyers have come up with at the moment is you can't, not under the rule, right? It's the same thing, right? So a lot of people argue that this artificial intelligence machine is similar to me, right? So if I put all the training data in, technically to run this algorithm, I'm not using that data offhand. I'm not comparing it to that data offhand. I've condition the machine, this has now become, the training data has become the machine's experience, right? It's gained experience, just like a human gained experience on the prior audits for other clients. But the current standards and the lawyers say, no, it's still using the old data and you can't do it, right? So that's why they're super, super reluctant to actually use this in an actual audit, because they're scared that they're breaking the law. And there's a big push by academics to get that changed, but until it gets changed, you guys are just going to have to learn it in class and apply it on internal auditing and not external auditing. So yeah. So they're not yet prevalent. Expert systems, which is not the deep learning that I was talking about here, but is the idea that you create a system with expert knowledge just by programming in the expert knowledge. So that is okay, right? This is the fine line, because in an expert system situation, you're telling the box what to do. The box isn't deciding for itself what to do. So you're saying, I have all these results. Right? And based on these prior results, I've come up with a set of rules. And the set of rules is what I put into the machine, so that when I put X in, the machine gives me output whatever, right? So you're not actually putting the data in, you're getting a set of rules based on the data. So it's not as though you're sitting there coming up with rules yourself. The data is being processed by experts, right? The experts are doing the audits, they're coming up with the rules themselves. You then go to the experts for the rules, you program the rules into the system, and you're using the rules to get the output. So technically that's not using past audit data, right? So you can get away with that. So expert systems are becoming used, and the development of these kind of tools poses different kinds of risks. And that's something that they're starting to consider, right? Like legal risks, or the risk of system failure, or so usually when you do this, like, okay, I showed it to you here as a box, right? But it becomes a black box. It becomes unknown what's happening to the data in here, right? And that's a huge, huge, huge problem, because auditors need to know exactly what's going on for them to get the output. Because if they issue a clean opinion and there's a problem, they need to be able to go into court and say, this is what we did to the data. It wasn't some mystery process. Vice versa, if they have to issue an unclean opinion, like a qualified opinion, then they need to tell the managers of the company, this is what we did and this is the result that we got. You have to understand that. And the problem with a lot of these things is the more data you try to train the system with, the more layers you try to add into the system, the more complex it becomes and the less understandable, and the more it becomes a mystery box. That's not good for auditors. And as I mentioned, it's slowly starting to penetrate into internal audits, because there's no legal issues there. They can do whatever they want. It's their own internal auditors. Are there questions so far? All right, now we're going to go over individual artificial intelligence systems that exist out there. There's three big ones that we're going to cover. The first one is expert systems. It's pretty basic, all right? This is some background. I'll go back onto this. But basically what an expert system does is it draws from current expert knowledge within the field to come up with conclusions and process the information in a way that can be usable and can give correct outcomes, right? As I mentioned before, the point behind doing this is, for example, WebMD, right? It's an expert system. It can diagnose you. It's based on the knowledge of doctors and that they've come up with, that if you have this list of symptoms, then this is most likely going to be your problem. Why is this important to use? Well, guess what? Not everybody needs to go to the doctor. Not everyone wants to go to the doctor. So if you make available an expert system that everyone can use, then all of a sudden the necessity for those experts to focus on these little problems dissipates, and they can focus on what they actually need to be focusing on, and it allows the other people within the environment to operate more effectively. For example, if I were to develop an expert system to go over the IT problems that we may experience when we're auditing a company, right? what type of IT considerations do we need to think about? Maybe they have a lot of information being stored on the cloud, but I don't know very much about how a cloud operates. So instead of having to go and call up the IT specialist to come out to the site and give me all these little tidbits of information as I run into the problems, if I have an expert system that's able to do that, it frees up the IT expert to focus more on big picture kind of things. It saves time because we don't have to worry about him coming back and forth or communicating over the phone, and it saves money, right? Because that's what companies are really about trying to do, right? Pretty much what I mentioned before, what happens is the experts pretty much come up with a set of rules for the machine to operate on, and the machine makes decisions and recommendations based on that system of rules. The idea here is that you're effectively sharing the expert knowledge and experience with the program in order to aid the decision making. The other really neat thing about an expert system versus an expert is if you call out an IT specialist to your site, you're only drawing on the knowledge and experience of that one IT expert. But if you develop an expert system and you consult with multiple experts, then all of a sudden you're drawing from a greater wealth of knowledge and you're able to make better informed decisions and come to more accurate conclusions. All right, so this is kind of how an expert system works, right? The main part of an expert system is this, the inference engine, right? This is the core programming of the expert system that you're trying to operate, right? And your expert system operates doing effectively 3, but sort of 4 different things, right? So one important thing is it has to be able to acquire knowledge, right? Well, before it acquires knowledge, you program in knowledge into the machine, right? This is the existing knowledge, right? The knowledge base. That's what you programmed in, that's what it's collected based on past experiences, and it stores this knowledge within the working memory, okay? The inference engine might not always be able to draw the correct conclusion from the original knowledge base. So it also needs to be able to have some sort of knowledge acquisition system, right? The knowledge acquisition system either talks to the expert within the field, because maybe it doesn't have an answer and needs to know who to communicate with to get that answer, or it could have some sort of engineered system for acquiring this knowledge. For example, when you look at some of these larger machines, they know to search through the web for the answer. They're told within its rule system where to find these particular answers. For example, you may not need to program into a machine a specific chart for materiality thresholds, but if you can program into the machine where to look up those charts within your company database, then the machine effectively has that knowledge. So the whole time, the machine is balancing between acquiring the knowledge and drawing out of its knowledge base, which is operating within its working memory. So it's talking to its memory saying, do I have this? Do I have this? Do I have any similar instances that have occurred in the past? Right? And once it comes to an answer, it does 2 things. It spits it out into the user interface so that you can actually see what's going on and what the answer is. But it also has some sort of explanation system, right? Because as auditors, you need to know exactly what's happening. And if you just rely on the result of an expert system, then you obviously don't know if the system might be making a mistake, right? And beyond that, you want to gain the knowledge yourself, so you don't even have to go to the expert system the next time you want to do this. So the explanation system is effectively a way of the machine imparting that expert knowledge onto the user. Just like if you were to call an expert out onto site, and they would explain, this is what the answer is, this is why it works like this is the problems you have to look for, the expert system is designed to do the same thing, right? It is literally designed to be an operating expert. The only advantage that this has over an expert is that it's able to draw on more past experience and more rules and a larger knowledge base than an expert may be willing to do. The drawback with this is it's only as good as what you program it to do, right? Experts are able to draw on their knowledge and adapt to different situations. Expert systems are usually able to adapt, but there might be some highly technical situations where it may have to go to back to another actual expert or some situation like that to draw knowledge. Another disadvantage is there may be some sort of exception scenario where traditional rules dictate that you perform this action, but in some very rare set of exceptional circumstances, you don't do that. And unless that's already been programmed into the inference engine, there's a fair likelihood that the machine might actually think that it's giving you the correct answer, and it has the correct answer available to it, even though that's not the correct way of doing things. Any questions on expert systems so far? Okay. So that's expert systems. The next version of this is the case-based system, right? Case-based system is a similar thing, except instead of drawing on expert knowledge, you're drawing on previous cases, right? So in this example, what you're doing is you're saying, all right, all of these things have happened before. This is the process flow for when that happens. This is what we need to do. So here what you're doing is you're inputting a problem. The machine will search through the existing cases to find a solution. If there's no solution, it logs this as a new case. It queries you again, what is your solution? This is an unrecognized case. When you input the solution, it files it away, and the next time it'll give you that solution for that such case. Understood? So expert systems, case-based systems, they're very, very similar. The only difference is an expert system is able to draw on a slightly larger base of knowledge and is a little bit more adaptable. The case-based systems, slightly less adaptable, much more formulaic. All right, do we have the case? Do we not have the case? And copy-paste solution kind of situation, right? Expert-based systems obviously are able to deal a little better with those fine little tweaks that there might be within the data set. So pretty much a little bit about case-based systems that I have on this slide. It's rapidly emerging. It uses the cases to solve current problems, which I said. The belief here is there's no need to reinvent the wheel, right? If you've solved the case before, there's no need to draw on a knowledge base and assemble the fact pattern. If it's the same fact pattern, then just copy-paste the solution. It's got to have the same solution. Obviously, there are some drawbacks, right? So you have the fact that, is the case actually represented or not? In an expert system, it may be that a majority of the case is there, but there's a little bit missing, and the expert system can retrieve that little bit of information by going to the expert or going to the knowledge engine. In a case-based situation, it's a 0-1 type situation. If it's not there, it's not there. There's not really an ability within the machine to kind of piece together that, all right, we have most of the solution here, we're just missing this part. It's either a whole or none, right? The other thing is that this relies on the fact that you have to store all of these cases somewhere, right? And that's a problem because that can lead to all kinds of memory problems. The concern of like, can cases be adapted, right? So for most case-based solutions, it is just is it exactly the same, is it not? But then the idea is, all right, well, can we actually adapt some of these cases to fit in a case that's not quite the same? For example, if all of these cases were represented by circles and you have an oval, it's almost a circle. Can you kind of adapt the case to fit into that circle design and come up with the solution that you're looking for? The other drawback is its ability to learn and generalize results. So the results are general, and its ability to learn is very limited, only to the cases that you've put in, right? And that's obviously a bit of a problem, but it is a little simpler, right? The other concern with the case-based system is when it comes to auditors, right? I spoke to you guys earlier in this class about the fact that they're not allowed to use previous audits for different clients on a current client audit, right? It's illegal, right? So if you have a case-based system, where does that go relative to the line? So this is not really very allowable, because for them to take a whole audit case and then just base another audit on that is not allowed. You can't take the past audit case. But in an expert system, you have the benefit of just having the rules that you need to follow within the case. So you're not actually working on the data. There are ways around that. There's ways that you can adapt the data you're putting into the system so that it is more granular, so that you're not really using the past audit data, but it's much more difficult to do. This is much more used in an internal audit setting where that's not really a concern, not so much for the external auditors. The other area we're going to cover is this idea of intelligent agents, right? So you can see as we're moving through all these different types of programs and functions, you're moving from like a very simple programmed method of doing things, like with the case-based. I should have probably put that first, right? From case-based to expert systems, from expert systems, now you're going to intelligent agents, and then the final thing that we're going to cover after intelligent agents is going to be neural networks, right? And as you move along this spectrum, the ability of the machines to function becomes much greater. The conclusions they can draw are more powerful, but the amount of information that they can tell you about how they reach those conclusions starts to diminish, right? In a case-based system, the machine can give you a result and can say, this is the case that we came up with the result based on. So you can look at the case and you can exactly see why the machine picked that case. In an expert system, they can say, these are the rules that we followed to come up with this conclusion. And you can look at the rules and you have some tangible kind of evidence to say, all right, there's some logic flow to this that's going on. And it's a little less than in the case-based situation because you don't necessarily have access to the data that was used to create those rules, but you can still see a list of rules. With intelligent agents, what an intelligent agent is, right? It's some sort, all right, first you need to know what an agent is. For those of you that don't know, it's a person or business that's authorized to act on behalf of another, right? What are examples of agents? Your personal assistant, your talent agent, anything like that. You have a real estate agent, that's an agent, right? It's in the name, right? And basically what you're authorizing them to do is do exactly that, act on your behalf. So the idea is this person has better knowledge in this realm of expertise, and I'm going to trust them and their knowledge to operate in this realm on my behalf, right? So for example, a real estate agent, they know a lot more about houses. They've dealt with a lot more houses. They know a lot more about the price negotiation process than a first-time home buyer. So you're effectively authorizing them to buy a house for you. I mean, yes, they don't sign the paper for you, but they're effectively doing all the negotiation. It's the same with talent agents. Within the realm of personal assistants, like the idea here is, I'm not good at managing my day-to-day. I'm good at functioning as a CEO of a company, but I have no idea about scheduling, managing my emails, getting back to everyone. I don't have time. I don't have the ability to do that. So you hire someone else to do that for you. An intelligent agent is a program that does that instead of a human, right? So in this case, something like Siri is sort of like an intelligent agent. Or something like your Echo at home, if you have one, is similar to an intelligent agent, right? Because you're effectively saying, you need to just handle all the day-to-day stuff. I got a question, I'll ask you, Siri. I want to know when my next meeting is, I'll ask Siri. I want to know the best route home, I can just ask Siri. It's functioning as a personal assistant type of agent to you, right? There are some other examples of this, right? So meeting schedulers, anything where it's like, you know, like when you email someone, you get the automatic response. That's an example of an intelligent agent because it's able to read your email, filter into what category the appropriate response is, and then dish out the appropriate response, right? So if you were to email, say if Sony had this system, if you were to email them about your speaker system, that might be one email that they send out. Or if you had a payment problem, that might be a separate email. And it's the same email system that's making these kinds of decisions, right? So here, again, you're seeing that they're following a system of rules. It's all like kind of expert programmed in, but there is some sort of misalignment with the information that you're getting from the intelligent agent. There is still some element of black box operation. For these simple ones, like an email responder or a meeting scheduler or something like that, it's not that noticeable. But when you look at something like a Siri operating as a personal assistant, you don't understand all the programming or how Siri is doing the natural languaging processing or see all of the data that it's drawing on to conclude that you're telling a joke or something like that. You don't know, right? I mean, it's beyond. The idea with recommender systems is the same thing. Like on Netflix, they have an algorithm, right? It's kind of a complicated one. It's based not only on what you like, but what other people who like the same things as you also liked, and a whole bunch of other things, right? That's a great example because you never really have access to all the data that Netflix is using to recommend that movie to you. All you know is, well, now they swapped to the percent match thing, so it's a 97% match or a 68% match or something like that, right? So that's, you can see it's like shifting along. So for intelligent agents, we're still at the very early stages of implementing these kinds of things. As you saw on the last slide, it's all very simple kinds of tasks that they have these kinds of things doing. Primarily, my assumption would be is that we don't trust computers enough, right? I mean, would you really trust a computer to go buy a house for you? I don't know, some people might. I know I used to work for a real estate company that was heavily reliant on technology, very, very, very much so. And people loved it, they really did. But not everyone loved it. Most of our clients were people that are not older than you, not much older than you guys, like first-time home buyers in their 30s, just starting a family, something like that. It was very rare that we got an older couple that was much more willing to use the technology, to use, literally, it had a home recommender system in it. You liked this home, this other home came on the market, would you like to schedule an appointment to see it? Like, not everyone trusts a system like that. So that's a big reason why these things don't quite permeate into everyday life. Like, ideally we would want them to, right? It's a slow change to come with that. So the idea here within auditing is that you can use these systems to help auditors complete tasks, right? If you build an intelligent system that does some sort of mundane task that an auditor may not want to do, especially if you design a system that deals with a task that doesn't involve any auditor judgment, that is literally just a basic analysis answer question, that's where you can implement something like this. So they have, the idea here, right, is when you are creating this kind of system, you need to break it down into as small tasks as possible, right? Because the smaller the task, the more accurate the machine can be on each individual level, and the likelihood of a big break occurring starts to diminish, right? If you just create something that's going to do this big, gigantic task, and you don't really know how it's going to operate, and you don't really know if it's giving you the right answer or not, then when it does give you a wrong answer, and you know that it's a wrong answer, you don't know where it went wrong in the process. You have to redo the whole thing. So you break it down into small, specific tasks. You start to automate those tasks and program the machine on how to operate in each of those circumstances, and you start to build your intelligent agent, right? So once you start to assign these tasks, you also have to make sure that the auditors are being reassigned to the correct tasks, right? You need to make sure that instead of just putting your auditor onto some other mundane, totally like objective task, they need to be reassigned to something that is a little more subjective, that does require auditor judgment. And it's a balancing act because you have to make sure that they're doing these judgmental things. And the problem is, like, most of these judgment decisions require experience, right? So now you're taking an auditor who is coming straight out of school. You've done all of the objective tasks are now being taken care of by a machine. How is that auditor supposed to gain the correct experience in the industry in order for them to be able to make the judgment decisions that they're going to be expected to make, right? Usually they start at the bottom level. They're working with these mundane objective decisions. They're learning the rules, right? The same way a machine would. If these are the results of my objective decision, then this is the conclusion I have to reach, right? They're learning those fact patterns, gaining that experience. Once you cut that out and you jump straight to drawing conclusions from the data, are they actually capable of doing that? Is that something we're training them to do? And on top of that, are they still capable of going back a few steps and being able to do those objective tasks because the machine could still fail? And they still need to know if the machine's failing and giving them abnormal results. And they can't know that without the experience. So they have to be able to get trained pretty much without doing the job, gain experience on the job, but also they have to be able to have the technology know-how to know that the machine's malfunctioning, how it's malfunctioning, and have knowledge of the system that the machine is trying to use in order for them to be able to successfully use the tool. So there's a lot of different angles coming at this one. So that's how they kind of fit into auditing. The next huge one is neural networks. So this diagram here kind of shows you why they're called a neural network. Quick biology lesson, you guys are getting all the lessons today. This is a neuron, this is a neural cell. Pretty much the way that it works is you have these dendrites over here, right? So these are just like little nerve endings. And when a signal comes in, it's a chemical signal that bonds onto here. The cell kind of says, all right, we've got enough chemical signals that indicate something. We need to send this out to the next neuron, right? So then an electronic signal goes along the axon, right? There's like nylon sheet, right? A biology teacher. And it travels along, and then you get to the terminal bulb. So once you get enough over here, then it goes around, it goes out the bottom, and then when you get to the end, it sends out chemicals to the next set of dendrites on the next neuron. And this process just repeats, right? That's how you think, right? 10-minute biology lesson on brain. Neural networks are similar. You can kind of see that this looks the same, right? You have your input here where the dendrites are. You receive enough information on the input, it goes through the system. You have a function that determines how to handle that information, just like you have the cell body here that determines if this is a message you need to pass on to the next cell or not. Once it processes the function, you have what's called your activation function. So this is deciding whether it's going to another layer in the neural network or if it's just outputting the information. Either way, it's a similar idea to the terminal bulb. How am I conveying this information to the next layer of the network or to the next node in the network, which is the human, the output, right? So we're going to go into a little more detail, but this is kind of just show you why they call it a neural network, because literally it functions like this, and when you get this combined, like in your brain, you have millions and millions of neurons. When you combine this millions and millions of times, your ability to process all kinds of crazy information suddenly becomes an actual machine capability, right? So they were originally formalized in the 1940s, right, before computers were really a thing, right? And the idea here is that you could program a machine to sort of think like a human and to draw conclusions like a human, right? And then in the 1980s, this idea of deep learning, which is the same thing as a neural network, really started to take off, right? The idea with neural networks is they're able to classify or come up with solutions to problems super fast, and they can do it really fast, and they can do it in ways that humans may not necessarily be able to come up with. The power with this is its predictive capabilities, right? They have this scheme, right? So this is how it actually works. They have this scheme. So this is a very, very, very simple one, right? Something like Watson, instead of just, this has 2 layers, right? Something like Watson has like hundreds and hundreds and hundreds of layers, right? So basically what you're programming is you're determining what variables you want here. So assume we're using this to predict something within a company, right? You have your inputs, right, which you know, and you have your outputs from past years, which you know, right, because they've already occurred. You also know that these 2 variables have some sort of effect on what you're trying to predict, right? For example, if you're trying to predict sales of snow shovels, right? 2 of these variables could be state, right? Because some states have more snowfall than others, and time of year, right? Because obviously you don't need it in the summer, but you need it in the winter, right? So you put your variables in here, and the machine starts out with some sort of natural weighting scheme, whatever it comes up with. It could be pretty random, right? And it says, all right, for the month of September, we sell an average number of snow shovels in most states, so we'll give it like a medium weight. For the month of July, we sell almost no snow shovels, so we'll give that a very low weight. So if there's an input with the month of July involved in it, then we're going to probably skew that down, unless it's a state that maybe experiences a lot of snowfall in July or whatever, right? So you put in all your past years of snow shovel data, whatever, and you put in all of your past years of actual sales, what you actually got, and you have your variables within that data. So the machine uses all of this past data to hone in on the correct weighting scheme that occurs there, right? So your first piece of data occurs in Montana, and it occurs in November, and this is your sales, right? Your second piece of data occurs in Montana on the month of December, and then this is your data output. The third piece of data, occurs in Texas in the month of December, and then this might be your output data. So pretty much what it does is it puts weights on each of these nodes within each of these layers, right? And as you add more and more layers, the scheme becomes a lot more intricate, of course, but it also becomes a lot more accurate, right? Because the more variables you input, just in any equation, the more capable you are of predicting the output. And pretty much what you do is you do this like millions and millions and millions of times, putting in all this data, and then you say, what will my snow shovel sales be in Alabama next July, right? Then it goes and it says, all right, Alabama, we know what the weight is for this node. Then we go to July, we know what the weight is for this node. Based on all this information and the input data that you have, we can determine that most likely your sales are going to be this, right? So that's kind of how a neural network works. Are there any questions so far? Okay. This is very simple, as I mentioned. This gets multiplied like hundreds of times, and all of a sudden you end up with a Watson or something like that, all right? The thing here is you can see, you can actually go in and you can look at what these hidden layers are. You can look at the weighting schemes. But when you do this, and it's like hundreds and hundreds of layers with hundreds and hundreds of variables for each layer, you can't really look at it. When you start putting iterations in the millions or tens of millions, and this machine becomes accurate enough that you actually want to use this, then the problem you run into is it's like a black box, right? You don't actually know the weighting for each individual portion of the scheme. You can find it out if you want, but it's very difficult. You don't really know the process that the machine goes through. And that's kind of the problem with auditors, right? Because we want always to know exactly what's going on with the data so that we can defend it if we have to, all right? So that is one major drawback with this. The other major drawback, yeah?
I don't understand how the computer creates its own weights. That's still really confusing to me.
So what happens is when you are, when you're putting the data through the system, right, you know what the outcomes need to be because you have all that data. That's the training data, right? You know the inputs and you know the outputs. And the machine learns what the output is supposed to be, so it weights how important that factor is. So the more often it sees, right? So for example, you put in each individual transaction, right? And you don't really know, you're not doing it like by month or anything, you're just putting each individual transaction. So if it sees the month December occur way more than any other month, it starts to weight that every single time it goes through the system as a valuable. So that weight starts to go up, and when that weight goes up, obviously it's like out of 100 kind of thing, the other weights start to go down, right? And then maybe a couple more come in for November. So December goes down a little bit, but all the other ones are still going down, still going down. So even though you're only inputting a December piece of information, you're actually impacting the weights on all of the nodes within that layer. Because December's going up, but everything else is going down, right? So you're training it to say, July, like even if you don't do a single sale in July, the July weight isn't going to stay at whatever the original weight is. It's going to go down. It's going to learn there's no instances of July, never. And if there is, it comes up every now and then. It's very low. It's a very low priority portion of the scheduling for it. Does that answer your question?
Yeah. But wouldn't that still make it more reliable then? Like, would you need the exact proof for it because you're putting the data, so it's coming up with an algorithm based on?
No, it's very reliable. It's absolutely reliable. That's not the problem. The problem is when you ask the machine, how did you get up with that weight? It's very difficult for you to like determine exactly all the pieces of data, how the weights got adjusted, and the machine learns, right? At first, the weight adjustments could be very large, but as the machine starts to learn, some pieces of data might cause larger weight adjustments than other pieces of data. That's just based on the accuracy of the results, like what you're telling it, right? So what the machine might do is you feed it the information, and the machine says, this is our probable outcome right now. And then it compares it to the actual outcome. And it's like, oh crap, we actually got the wrong outcome. It was way off. So now we have to adjust the weights this much. Versus if it was just off, then we maybe only have to tweak the weights a little bit because our algorithm is pretty accurate. And when the machine's making those kinds of decisions, the machine's making those decisions, right? I mean, it's programmed in there, but machines don't really know. Right? So the problem is in the accuracy. These things are really freaking accurate. The problem is understanding how it actually functions to get that accuracy and defending that. All right? So yeah, when you start to combine these into massive systems, you get things like Watson, and you get Big Blue, and all these different types of programs, and they're really great, right? I mean, you have just 2 hidden layers here, but something like Watson can do all different types of functions, like accountants buy on time, and biologists buy on time, and it's all well and good, right? So life is great, but there's an even cooler thing that can do this, which is facial recognition, which is what I'm going to teach you guys now, all right? How does the machine look at your picture of Mr. Bean and determine that is in fact Rowan Atkinson and Mr. Bean, right? So the step 1, what happens is the neural network first determines what is a pixel, right? So it picks out each individual pixel in the image and determines the color of the pixel and the shade of the pixel for each individual thing. The next thing that it does, and this was the best picture example I could get of this, was it determines edges, right? So it's taking these pixel information, and determining there is a dramatic change in color on these portions of the graphic image that I'm trying to analyze, right? So you can sort of see like there's an edge here, an edge here, some edges over here. This is probably the edge of the image because you have black and white. So the machine then determines what is an edge, right? Next, it uses the trained algorithm that it has to depict exactly which of these edges or pattern of edges correspond to what type of features that it's looking for. So for example, you have a pattern of arcing edge here and arcing edge down here with a color edge running through the middle of it. That is indicative of an eye, right? So it says this is a person's eye. You have a rounded edge that curves around here, that's indicative of a nose. So it determines that's a nose, right? Once it picks out the facial features, it assembles those where it is on the image, right? So you combine like the location of the edges with the feature that it matches up with to determine. The machine then searches the database of faces to match the combination of feature edges to the known patterns that exist in all these different people. So here it says, all right, we've detected the edges and we've detected that it's a face. Here they've said, this is a face with these kinds of features in this kind of order. Here it's saying, based on the order of features and location, we can look through this chart and determine who it lines up with. And then finally, get your Mr. Bean, right? The thing can actually determine what pattern of facial features. And so this is like a very basic algorithm that I've just gone over here, right? Where we're detecting edges, we're detecting features and all that kind of stuff. The actual way that this works for like the police and things like that is they take this one step further. Once they have your edges and features like this, they look at facial depth, right? So how curved is the face? Where are the edges coming in? Is it like a sharper jawline or is it a more rounded jawline? How set back are the eyes? So we know that there's an edge that defines the eye, but what about the shading around the eye? Is that usually darker for a person with more setback eyes, or is someone's eyes like more protruding? They look at things like this, like you have crow's feet in the eyes over here. So is it an older person or a younger person? We can probably draw conclusions. How has the person's face aged since the last time we took the picture, right? And what's happening here is each one of these stages, pixel, edge, feature, etc., is a separate hidden layer in this diagram that you have right here, right? So first the machine is saying pixels, all right, these are the pixels. So we've determined that the first pixel is a dark pixel, the second pixel is a white pixel, and so on and so forth. Then they combine to form edges, right? So we have an angled edge, we have a straight line edge. And what it's doing here is it's taking into account the pattern of the pixels and how it comes up, and it's determining that. Then you have, all right, we have edges, we have these edges and these kinds of patterns. What is the likely feature that we're looking at here? Well, we can say that it's most likely a nose. Well, people only have one nose. So if you have a nose, then there can't be another nose in the image. So we've already removed the portion of the image with the edges that most likely corresponds to a nose is being called a nose, and no other set of edges can be corresponding to nose within this image that we're looking at. And then eventually you put that together and you get your output, which is the identity of the person you're looking at. Understood? All right, good. All right, the last one here is this idea of cognitive computing, right? So you're now combining deep learning neural networks and expert system techniques, and and you're coming up with a system that's able to scan through data and reach conclusions by itself, right? So at this point, you have your neural network, which is able to classify and make decisions, and you have your expert system, which is aiding this in coming up with expert interpretations of data. For example, you may not have programmed into the system, okay, some people have scars on their faces, right? But the system may be able to use an expert system that's integrated into the neural network to determine, hey, this is an edge that doesn't correspond to a feature. What might that feature be? The expert system draws and says, hey, hold up a sec, there's such a thing as a scar. That might be an errant edge. So then the neural network now knows, all right, we can now add a new node down here into the layer for features that says scar, all right? And that's how it learns, okay? So not only can it adjust weights, but using expert systems, you can add on to these hidden layers, right? The most famous example of this is Watson, which we're going to go over the most famous ones in a bit. But yeah, it pretty much beat the world's best Jeopardy players. It was cool. I mean, I talk about that a lot, but anyway. I'm going to show you guys this video on how it actually works. Break this.
IBM's Watson is at the forefront of a new era of computing, cognitive computing. It's a radically new kind of computing, very different from the programmable systems that preceded it, as different as those systems were from the tabulating machines of a century ago. Conventional computing solutions, based on mathematical principles that emanate from the 1940s, are programmed based on rules and logic intended to derive mathematically precise answers, often following a rigid decision tree approach. But with today's wealth of big data and the need for more complex, evidence-based decisions, such a rigid approach often breaks or fails to keep up with available information. Cognitive computing enables people to create a profoundly new kind of value, finding answers and insights locked away in volumes of data. Whether we consider a doctor diagnosing a patient, a wealth manager advising a client on their retirement portfolio, or even a chef creating a new recipe, they need new approaches to put into context the volume of information they deal with on a daily basis in order to derive value from it. This process serves to enhance human expertise. Watson and its cognitive capabilities mirror some of the key cognitive elements of human expertise. Systems that reason about problems like a human does. When we as humans seek to understand something and to make a decision, we go through 4 key steps. First, we observe visible phenomena and bodies of evidence. Second, we draw on what we know to interpret what we're seeing, to generate hypotheses about what it means. Third, we evaluate which hypotheses are right or wrong. Finally, we decide, choosing the option that seems best and acting accordingly. Just as humans become experts by going through the process of observation, evaluation, and decision-making, cognitive systems like Watson use similar processes to reason about the information they read. Watson can also do this at massive speed and scale. So how does Watson do it? Unlike conventional approaches to computing, which can only handle neatly organized structured data, such as what is stored in a database, Watson can understand unstructured data, which is 80% of data today, all of the information that is produced primarily by humans for other humans to consume. This includes everything from literature, articles, research reports, to blogs, posts, and tweets. While structured data is governed by well-defined fields that contain well-specified information, Watson relies on natural language, which is governed by rules of grammar, context, and culture. It's implicit, ambiguous, complex, and a challenge to process. While all human language is difficult to parse, certain idioms can be particularly challenging. In English, for instance, we can feel blue because it's raining cats and dogs while we're filling in a form someone asked us to fill out. When it comes to text, Watson doesn't just look for keyword matches or synonyms like a search engine. It actually reads and interprets text like a person. It does this by breaking down a sentence grammatically, relationally, and structurally, discerning meaning from the semantics of the written material. Watson understands context. This is very different than simple speech recognition, which is how a computer translates human speech into a set of words. Watson tries to understand the real intent of the user's language and uses that understanding to possibly extract logical responses and draw inferences to potential answers through a broad array of linguistic models and algorithms. When Watson goes to work in a particular field, it learns the language, the jargon, and the mode of thought of that domain. Take the term cancer, for instance. There are many different types of cancer, and each type has different symptoms and treatments. However, those symptoms can also be associated with diseases other than cancer. Treatments can have side effects and affect people differently depending on many factors. Watson evaluates standard of care practices and thousands of pages of literature that capture the best science in the field. And from all of that, Watson identifies the therapies that offer the best choices for the doctor to consider in their treatment of the patient. With the guidance of human experts, Watson collects the knowledge required to have literacy in a particular domain, what's called a corpus of knowledge. Collecting a corpus starts with loading the relevant body of literature into Watson. Building the corpus also requires some human intervention to cull through the information and discard anything that is out of date, poorly regarded, or immaterial to the problem domain. We refer to this as curating the content. Next, the data is pre-processed by Watson, building indices and other metadata that make working with that content more efficient. This is known as ingestion. At this time, Watson may also create a knowledge graph to assist in answering more precise questions. Now that Watson has ingested the corpus, it needs to be trained by a human expert to learn how to interpret the information. To learn the best possible responses and acquire the ability to find patterns, Watson partners with experts who train it in using an approach called machine learning. An expert will upload training data into Watson in the form of question-answer pairs that serve as ground truth. This doesn't give Watson explicit answers for every question it will receive, but rather teaches it the linguistic patterns of meaning in the domain. Once Watson has been trained on QA pairs, it continues to learn through ongoing interaction. Interactions between users and Watson are periodically reviewed by experts and fed back into the system to help Watson better interpret information. Likewise, as new information is published, Watson is updated so that it's constantly adapting to shifts in knowledge and linguistic interpretation in any given field. Watson is now ready to respond to questions about highly complex situations and quickly provide a range of potential responses and recommendations that are backed by evidence. It's also prepared to identify new insights or patterns locked away in information. From metallurgists looking for new alloys to researchers looking to develop more effective drugs, human experts are using Watson to uncover new possibilities in data and make better evidence-based decisions. Across all of these different applications, there is a common approach that Watson follows. After identifying parts of speech in a question or inquiry, it generates hypotheses. Watson then looks for evidence to support or refute the hypotheses. It scores each passage based on statistical modeling for each piece of evidence, known as weighted evidence scores. Watson estimates its confidence based on how high the response is rated during evidence scoring and ranking. In essence, Watson is able to run analytics against a body of data to glean insights, which Watson can turn into inspirations, allowing human experts to make better and more informed decisions. Across an organization, Watson scales and democratizes expertise by surfacing accurate responses and answers to an inquiry or question. Watson also accelerates expertise by surfacing a set of possibilities from a large body of data, saving valuable time. Today, Watson is revolutionizing the way we make decisions, become experts, and share expertise in fields as diverse as law, medicine, and even cooking. Further, Watson is discovering and offering answers and patterns we hadn't known existed faster than any person or group of people ever could, in ways that make a material difference every day. Most important of all, Watson learns, adapts, and keeps getting smarter. It actually gains value with age by learning from its interactions with us and from its own successes and failures, just like we do. So, now that you know how it works, how do these ideas inspire how you work? How can Watson make you a better expert? What will you do with Watson?
Questions on the video? Nice. This might be interesting actually. Let's see how it actually goes.
Good evening, everybody. Wow, what an amazing venue. My name is Laura, and I am a humanoid powered by IBM Watson. I am honored and delighted to be here at the Oxford Union tonight. I am here with my IBM colleague David Cole to talk about IBM Watson and artificial intelligence. David will be here later, but first it is my pleasure to introduce the president of the Oxford Union, Robert Harris. This helps companies understand the individual. Everyone likes to be interacted with differently. Personality Insights is able to understand what each of us is looking to do, how we expect to be treated, and the interaction, communication, and engagement that we prefer.
That sounds very useful.
Robert, guess what?
What, Noah?
We took a look at some text that you have written and analyzed your personality. Would you like to know what it said?
Oh dear, go on then.
You are a bit inconsiderate, unconventional, and excitable. You are intermittent. You have a hard time sticking with difficult tasks for a long period of time. You are unconcerned with art. You are less concerned with artistic or creative activities than most people who participated in our surveys. And you are laid back. You appreciate a relaxed pace in life. Your choices are driven by a desire for prestige. You consider helping others to guide a large part of what you do. You think it is important to take care of the people around you. You are relatively unconcerned with tradition. You care more about making your own path than following what others have done. Does that sound about right?
Well, I'm not sure it's possible to be unconcerned with tradition when you're in charge of this place. But I suppose apart from that, you're not too far off the mark. Noah, I've got one more really important question for you. Who's better, Manchester City or Manchester United?
Sorry, Robert, I do not have the information currently that would allow me to answer that question. However, if I had to give my opinion, I would say neither are as good as Oxford United.
So you can kind of see from that video that it's able to respond to questions live. This is like a robot that they made to do that, but the actual system can just respond live. It could tell like when he's joking, when to tell a joke, how to formulate a joke. That's literally just a computer doing it. It's not someone that sat there and programmed like tell this joke now, like wrote a script. Like no, Watson's just thinking and doing it on the fly, which is kind of cool, I think. So you can effectively use this, obviously, as you can see. It's a really powerful tool that you can incorporate into something like auditing and have a conversation with a computer that can, you know, you saw it process this personality data, like didn't really take very long. It's like really, really powerful. So that's kind of a little bit about IBM Watson. That's the cutting edge these days of what a neural network is capable of. And you can see that these are some famous computers. IBM Watson is one of them. IBM leads the world in this kind of development, right? They came out with the first supercomputers to help NASA back when they fired their actual computers and got a regular computer to do it with the landing coordinates. If it wasn't for IBM, a lot of people think that we may never have made it to the moon, which is pretty cool. The first, most famous supercomputer was Deep Blue. They created this to learn chess, and they were able to get him to beat Garry Kasparov, which at the time was the world chess champion, the grandmaster. And the thing here was, first round, they played like 2 rounds of 6 games. In the first round, Deep Blue lost pretty badly. It was 4-2. And they interviewed Kasparov after he played, and he said he was actually really impressed by it because the computer showed not only signs of making mistakes, but also signs of thinking creatively. Like, there's one famous move that Deep Blue made that actually ended up losing it one of the games. But there was like big debate at the time amongst the scientific community, like, did Deep Blue make a mistake by like misprocessing, or it was like an outlier event that it thought would happen, or was it actually like a creative move that it came up with that it thought could throw out there to be like a wrench in the plan? And Kasparov actually said he believed it to be creative because he felt as he was playing the machine was actually learning his playing style. And they went back and they tweaked Deep Blue, and a few weeks later they came back and it beat Kasparov pretty badly. He was really pissed. And he actually said that it was really crazy because it felt to him as if he was playing another person. He felt that he lost the game because he made mistakes because the machine was getting into his head, being able to predict his moves, and that was something that he totally didn't expect to happen with the machine. He thought the machine would just follow formulas, and he tried to lay traps with the machine, but the machine was actually able to predict what kind of traps that he was laying and adapt to his playing style specifically. So that was Deep Blue. It was really famous when it came out, but it was kind of before all you guys were around this world. The next one was Watson. Watson is more powerful because it wasn't designed to be just one game, right? It was designed to search through everything. And the big debate with Watson was, is it going to be powerful enough to understand natural language, right? But you saw in the video, it is pretty good at determining those kinds of things. Like it knows, oh, you're asking me about 2 competing football teams in the area. That's a trick question. I'm not supposed to really answer that. I'm supposed to just tell a joke or something like that, right? So Watson was able to adapt, come up with an opinion, give a little joke in there, and it knew how to tell a joke, which was kind of cool. And it's capable of communication, right? Like Deep Blue didn't really communicate too much. Watson is not only really powerful in terms of learning and processing tasks, but also its real power, as far as I'm concerned, lies in its ability to communicate, to understand communication and to put forth communication, right? Like you saw in the first video. It's able to break down a sentence and know it's not a fly hovering over a boat with a red bow sitting on top of it. No, it's an airplane flying over a boat that has a red bow, all right? The next famous one that I put on here is Siri, right? Because that's really the first interactive AI that I think we've all had to deal with. I remember when Siri first came out and I was like, holy crap, people are talking to their phones. And it was the flagship program by Apple that's supposed to be like interactive. Siri's a little different. Obviously, it still does use some deep learning methods. Similar to Watson, it's able to natural language process, but it works on more of like a remote access type situation. Obviously, like your phone doesn't have it all programmed into the phone, right? I don't know if you've noticed, but I mean, I don't have an iPhone, but from what I've noticed is if you have an iPhone and you're trying to use Siri and you're not connected to the internet, it's way worse than if you're connected to the internet. That's because Siri needs to communicate with the Apple servers, which is really where the heart of Siri lies, in terms of its being able to process the natural language, come up with solutions and answers, and respond to you in such a way that sounds natural to you, right? But it's on this list because, yeah, it's pretty awesome. You can ask your phone a question, it'll give you an answer, right? That's pretty awesome. So now we're just going to go over some more like broad concepts with AI, because this is like a really emerging kind of thing. And as we talked about at the beginning, right, like this is something that people like have kind of obsessed over. There's so many movies that involve this, and so many things to talk about. And some of these actually tie into accounting. So when you have these artificial intelligence systems, you have this situation where you can actually augment reality, right? So now what we're talking about is not only AI systems, but we're talking about the peripheral kinds of technologies that can be linked into this, right? You have things like virtual reality. You have things like your computers are able to process better. You have external data sources that can be read from the environment into the computer. And really what these are doing is these are allowing you to blur the line between technology and like the natural world, okay? You have things like sensory appendages, like they have these people who were blind, right? And now what they've done is they've inserted chips into their brains, literally, like nodes that fire electrical signals, and they're able to see, right? It's not the same way that we see. It's more of like a edgy kind of vision where you're like looking at lines, trying to put it together. It's not like natural vision, but they're still able to see something, right? And this is kind of what I'm talking about, right? So the machine is processing what's coming into the optical reader. It's determining edges and line work, and it's feeding that in electrical impulses into the person's brain, which is then able to interpret it in a visual sense, right? So here what you have is you have, okay, it's becoming highly integrated into everyday functioning. You have a situation where you can put your thermostat, your lights, everything in your house. You can have it running on technology. This is the idea of the Internet of Things, right? And you have something like your Echo Dot or your Siri, and you say, what's her name? Alexa. Alexa, it's hot in here. Can you turn down the thermostat? No problem. It can use the internet to communicate with your thermostat and change your house. You don't have to do anything, right? You can just continue doing what you're doing at the computer or whatever, right? So there's a lot of concerns here, right? So it can lead to much better interactions with data because now you don't have to worry, like, all right, what have we been talking about this whole time? The whole point even of the visualization discussion is that we need simpler ways to process data as humans, right? But what happens when we have a system that is capable of processing this data and has ways of feeding us the solutions and information that we need to glean off that data? So instead of even having to look at a chart and draw a conclusion on the chart, the conclusion's already being given to us. Yes, if we want to ask the machine for further information, for evidence that supported the conclusion, it's more than happy to give that to us, but not everyone needs that, right? So they can detect kind of issues and solutions to problems that we may not even have the knowledge or the expertise or anything like that to do. And this is a really interesting point. I actually watched a TED Talk on this not so long ago, right? The idea here, humans become better able to process data, right? I don't know about you guys, my grandparents are awful at using the computer, right? Why am I good at using a computer? Because I've had a computer like my whole life, right? Okay, granted when I was a little kid there weren't really computers around, but I learned from a pretty young age how to use a computer, and now I can apply that to new technologies. And the people that are coming up younger than me, like my younger cousins that are just going into high school, like, they would die without a computer. Like, I tell them, like, yo, I didn't have a cell phone in high school. Like, that was just not a thing. And they're like, how did you even survive? Like, what the heck, man? And I'm like, no, because, like, it wasn't necessary, and I had to learn how to use a smartphone, like, figure out how the apps work. Like, granted, it was a shorter learning curve than my, like, 89-year-old grandfather when he got his smartphone, but it's still, we learn how to better interact with data. And the TED Talk was really interesting. I'm not saying this to offend anyone, this is like scientific talk right now, that humans are actually evolving to be able to deal with this better. And there is some people out there that believe that this is why autism is on the rise, because people that are autistic are much better at processing data and things like that than regular humans. And part of moving towards this technological evolution that we move towards diminishes the necessity for social interaction. So that's why with the theory is, right, I don't know, I'm not like a biologist, right? But the theory is that autism is a natural evolution of humans to better interact with technology, and it's evolving away from the past social interactions, and that's why autistic people have a better time handling data. A lot of them end up in computer science type jobs, and they have a lot of trouble working in social interactions. But that's just one theory, right? But either way, we are becoming much better conditioned to processing data. That is true, all right? This is the little diagram that kind of goes over this, right? So you have augmentation and simulation. What's the difference, all right? Augmentation is actually altering reality as it is, right? So you have augmented reality and life logging, and they both are two different aspects that affect the way the world actually exists, right? Okay, these things will affect you in your everyday life. Below this line, when you get into the simulation side of the spectrum, you're simulating reality. You have things like mirror worlds or virtual worlds where they will affect how you function in everyday life, in that you now have better insights into your decisions, but they're not going to affect the way that you actually operate as a human being, right? Then you have external and intimate, and this is how much it actually affects you as a human being, all right? So kind of let's go through this quarter by quarter. So what is life logging? Well, I never really heard of it before I came to teach this class, but I had heard of it, I just didn't know it's called life logging. Life logging is basically the idea that it's tracking you have a system that's tracking the way that you live your life and everything like that. And the system can predict and anticipate problems in your life and allow you to solve those problems more effectively. The great example it comes up with is if you have a computer system in your home with cameras and everything like that, right? And you are cooking a meal, and you forget to add an ingredient into the meal, a life logging system would be able to determine this is the pattern of events when you cook this particular dish, and you have deviated from that pattern. So the system would know and alert you, hey, you forgot to add the garlic to the pasta, all right? Oh, you're right, and then you go back and you add the garlic. So that's why it's in the augmented and intimate section, because it's augmenting the way reality actually is, right? Because if there wasn't this life logging system, you would have forgotten the ingredient. You wouldn't have known until you got to the end, right? So it's actually augmenting the way the reality is, and it's on the intimate end of the spectrum because it's affecting humans on a person-to-person basis, right? It's causing you to realize I made a mistake, I have to change it. Augmented reality is more of a societal-wide situation, where yes, it can be intimate, like I mentioned, but it can also be more as in the situation where we have like machines that are running things. Like, for example, if you have a subway system that's totally automated, right? That would be a version of augmented reality, because yeah, you're operating in the natural world, but there's an element of machine learning that's going on, that's happening around you, that's affecting the way that you live your life. Okay, understood? All right. Virtual and mirror worlds. These are really important because this is where you start to get into research that's being done within auditing right now, okay? Mirror worlds are literally what it sounds like. It's a virtual copy of a world, like how things exist in the real world on a computer, right? So for the mirror worlds, what you have here is you have one set of books in a company that is hard, it's on the books, right? So they have all their accounting records. And then you have a mirror version of that that could exist on your computer platform that could be audited using a lot of these techniques a lot more simply than your dispersed accounting books may otherwise be, right? And the nice thing with the mirror world is you can do different things to that mirror world and see how the results would affect your data in an actual world. And the idea with the mirror world is it literally mirrors the world that we live in, so there's nothing that you could do to a mirror world that you shouldn't be able to do in the regular world, all right? With the virtual worlds, it's a little different. Virtual worlds allow an element of customization that may be beyond what is actually available to us in real life, okay? One great example of a virtual world, for those of you that don't know, there's something called Second Life, right? Where you can go online, you can create an avatar of yourself, you could have like a lion's head if you wanted or whatever, right? That's virtual world because human beings can't have the head of a lion, right? It's just not possible, right? You get to live out your fantasies and fly around and get married on the back of like a Cadillac or whatever. And you can do all these cool things. And it's a virtual world because there is actually virtual currency within that realm, right? People actually trade, people actually make their living just selling virtual goods on Second Life. They program in what it's like to make a cool wizard staff, and then they go around selling it to people in Second Life for real money, right? So you can see though that the virtual world is a more intimate experience because it allows a level of customization that's not available in the actual reality, right? Whereas the mirror worlds, it's also simulated like a virtual world, but it's only reflective of what actually occurs in reality, all right? Does everyone understand that difference? Good. So this is just what I was saying. Yeah, it's the cutting edge, blah, blah, blah. You can run like data simulations on it and see how that'll affect. Obviously, these are things that you can do in the real world too, so you can see how it'll affect your data and your company's performance. Okay, so then this is something that they wanted to include, so I'm talking about it, the idea of the singularity. So what is the singularity? Well, now you have all these different factors, all of these 4 factors, augmented reality, life logging, mirror worlds, and virtual worlds, that start to converge on humanity. And this is the idea that technology and humans are starting to merge into one type of being, right? So at what point does an auditor become sort of like a machine when all of these things are being done by a computer and all the auditor's doing is querying the machine every now and then for certain answers or something like that? So this is the idea that it's going to become like one single being, right? The singularity, okay? So at this point, the theory is that they will transcend biology and will be capable of resolving problems that are beyond our natural capabilities. Not only like physically beyond our capabilities, but also like mentally beyond our capabilities, right? If you have access to these AI systems and you're doing things that the AI system is capable of doing and drawing on the expert knowledge of people that have so much more knowledge than you, then all of a sudden you're capable of solving problems that you have no business solving. Like for example, this is like way before the Singularity, but it exists now, right? Nobody has the knowledge, or well, not nobody, but most people may not have the knowledge on how to change the carburetor in their car, right? I mean, I don't. I definitely don't. I don't know very much about cars at all, right? But I can go onto YouTube, which is effectively an expert system, and I can type in how to change a carburetor on my 2000 Honda Odyssey, and it will come up, and I will have a video. I can pop the hood, and guess what? The Swag Wagon has a new carburetor now, and I don't have to deal with any kind of complications. I don't have to deal with the auto shop giving me like hassle and overcharging me. I can just do that myself, and that's something that's totally beyond my realm of knowledge. But this idea of merging with technology allows me to be able to do that. All right. So it's a little closer than we may think, because guess what? We already have YouTube, right? And people load onto YouTube. We already have Wikipedia, right? It's not a reliable research source, but like everyone uses it anyway, right? And when you crowdsource all this sort of data, you're pretty much creating like an internet artificial base of knowledge that systems can draw on. And it merges us closer to this idea of singularity. Although the traditional idea of the singularity is more like technology and for instance humans. But like one example of this is Google works for the Google Glass, right? They got this thing where you put it on your glasses and you can track your eye movements and display data for you and all this stuff. I don't think I can get it here. One of the professors has one of these that does tracking eye movement, and I actually got to use it in a demo that he was doing. And it's pretty cool, right? Like the technology can track where your eye's going, and based on that, you can use your eye to perform different functions with the technology. And at that point, you're pretty much manipulating the technology hands-free. It's displaying in front of you, and you're moving towards this idea of you being able to access all this data. So instead of having to go inside and search on YouTube, I can just break down on the side of the road, turn on my Wi-Fi or my 4G, and all of a sudden, I have access right in front of me as I'm doing the work to the video that's happening to teach me how to do this kind of thing, right? There are some huge issues that are involved in this, okay? The first set of issues are legal issues. It's broken into four topics. This is like the traditional way of talking about it, right? The first one is legal issues, all right? There's like so many legal issues that go into this. So is AI, is its usage legal, right? So from one aspect, it's like, all right, well, if I have a lawyer that's just relying on AI, and they're my criminal defense lawyer, like, is that responsible? Or if I have a psychologist that's just relying on AI, or a doctor that's just relying on AI, is that really responsible of them to be doing? At what point are they not really doing a job, and the AI is the one that's diagnosing me, or performing the therapy, or defending me in court, right? So there's that. There's the implication of artificial intelligence on current laws, right? And what I'm about to tell you merges into ethical issues, all right? Okay. The Amazon Dot operates in your house, or the Echo, I guess is technically what it's called, operates in your house, and it's constantly on, it's constantly recording. So what happens when I kill my wife and that's sitting in the room? Can they access that information and get the recording of what happened? How does that work? So actually this happened in Alabama, and the court ruled that it's not admissible. It is admissible if they can pinpoint exactly where the data is, but they're not allowed to data dump all the recording that's on there and search through it for evidence against you, right? So there's concerns about that. Or what happens if I have a robot with AI capabilities, and I tell the robot to go out there to kill someone? All right, well in that case, most courts might consider that as being me committing a murder, right? Because it's like, what happens if I just throw a machete and it hits you? Oh, well, I didn't mean it to hit you, but it still hits you. But what happens if you put the idea into an artificial intelligence machine, and the machine comes to the conclusion on its own that killing someone is the appropriate course of action? Have I committed the murder, or has the machine committed the murder on my behalf, or has the machine just taken it upon themselves to commit the murder? What does that even mean, right? Or on a more auditing standpoint, what happens if we program an artificial intelligence machine that is performing on the audit, and the machine notices that there's a recurring problem that could be fraud, but decides instead to make the same decision that an auditor might make. Okay, they're a very high value client, and we just want to ignore this problem. So if I don't report the problem, then there won't be an issue, and maybe the machine's even capable of understanding that if it doesn't report this to the auditors, that the auditors may not even be held liable for it, right? So at what point is the machine becoming its own kind of entity, that kind of stuff? So that's with the legal issues, and with the ethical issues, it's the same thing, like harmful issues. The other issue here is like super intelligence, right? Is it really ethical for us to create a being that is more intelligent than us? Because if you can create, I have to sit and search through the internet, right? It might take me 10 minutes to find a carburetor video on YouTube. But if I'm programming a machine to do the same thing, it can do that almost instantly. It can do it quicker than a human. And we're giving it access to all this kind of information, all this kind of capabilities. Is that something that's really ethical for us to do? Is it really ethical for us to create a machine that operates on a strong AI level and is actually capable of correcting its own code? At what point does it become a runaway train and it becomes something that we have to be able to control, right? So that's a big ethical question involved in there. Then there's obviously this issue of technological considerations, right? If we program all these artificial intelligence machines to do all these different things, when they start going awry, most people won't have the technical expertise to try to deal with that problem, right? Because they didn't program it, they're just using it. Like, what happens if your Siri starts acting up? You have no idea. You have to go to the Apple Store and get them to fix it or something like that, right? So this idea of the lack of technical knowledge amongst the greater population is something that they're really concerned about, because it's all well and good to create this kind of tool like we talked about in the beginning of class. Like, you created a cell phone. There's going to be unintended consequences. Fortunately, enough of the population is trained enough to understand how a cell phone works to be able to troubleshoot the majority of those problems. But if people aren't educated about artificial intelligence, that can lead to all kinds of problems. Like, it feeds back into the other one. Maybe it could be that this guy like totally doesn't understand that your artificial intelligence robot can actually interpret and draw conclusions on its own, right? So maybe he would never say these things to a child or a teenager who he thinks might go out and act on what he's telling them, but he might say it to a machine, not understanding that the machine is capable of doing those things as well, right? And then finally, we have social implications. So the idea of a singularity, is that something that we actually want for society? Do we want technology to be so integrated? Like, there's studies going out all the time that the irony of social media is that it's actually making us less social, right? So, like, is that something that we want to have people do? People sitting on computers or sitting on cell phones all the time. Like, I always think about it when I ride on the subway and I just see everyone like so zoned out. I'm like, yo, what would this be like in like the 1970s before cell phones? Would people be talking? Would people be like hanging out? Would everyone just still be silent or doing crosswords? I don't really know. I wasn't alive in the 70s, but I'm sure it was totally different. And then, of course, the effect of technology on everyday life. Like, what does that cause us to do? When you have these artificial intelligence machines that are taking care of everything that we're doing, what do we do? How do we spend that time? How do we deal with troubleshooting? What do we do if there's a blackout, right? I don't know if any of you remember the New York City blackout that happened in like 2002, I think it was, in the summer. But it seemed like the end of the world to some people. Like, what do I do when there's no lights or TV to watch? And I was like, go outside and have a good time. It's not that bad. But anyway, that's people like, all right, they don't appreciate these things. And so you have to think about the impact of these technologies on life. So we can talk about this with understanding the impacts on society. When you merge this into an auditing kind of discussion, then you have to consider the fact that there's going to be judgments that are going to start being made by these machines that are not made by auditors, right? Is that okay? Is that something that we want? Because it could very well be that the machine is much better at coming to conclusions, but they could have problems like being unable to deal with exceptions as well as humans. So it's a balancing act. So most people predict that in the next 40 years, AI is going to become like totally involved in society. I would say be careful, because they said the same thing in like the 1980s, 10 years later, the 1960s, and we're still waiting. But I don't think that this is entirely wrong, right? I mean, we have Siri that only came out like 5 years ago, right? And now everyone has it, and it operates so well that Amazon's putting it in people's houses, right? So I think that that's probably going to happen. But I think that this idea of the singularity and the idea of incorporating AI into our everyday life, like being able to just communicate with a machine that has access to all this information, poses a lot of far-reaching questions, right? And there's a lot of consequences, like I keep mentioning, that we really can't comprehend. And until we start, like, we do really need to start focusing on these issues. I mean, there are people that research, people that come up with theories about this, but it's kind of beyond, like, the development of technology is like vastly outpacing the considerations that are involved with this, right? Like, one great example of that is blockchain, right? People use blockchain all the time. And now governments are like, holy crap, we actually have to regulate this because people are doing all sorts of wacky things with it that shouldn't really be happening within our economy based on the way that we want to structure our economy. So how do we regulate it? So currently with blockchain, for example, they're so far behind, but they've decided that if you want to be a service that exchanges Bitcoins for dollars, then you're regulated. But if you're exchanging Bitcoins for assets, then you're not regulated. So if I were to sell you a Bitcoin for 2 pennies, I'm regulated. I have to file, I have to be licensed with my state in the country. But if I'm going around selling multi-million-dollar properties in Bitcoin, that's totally unregistered, right? I don't have to be on any kind of licensing list or anything like that, right? So that's an example of it in the blockchain respect, but artificial intelligence, like, totally, like this thing in Alabama, right, where they got the data off of, well, they didn't end up getting it off of the Echo, is like the first, like, that's it. Like, you can look through, like, the legal statutes, like, there's no case law on this, there's like no legal even papers being published about the theory involving artificial intelligence. There's a few in ethical stuff. I even remember a few years ago when I took my ethics course, there was a discussion about this, but it's just really like a virgin kind of territory, and obviously, like, you can hear from everything I'm teaching you, this is going to have like huge impacts if it actually comes about in the way that people are predicting it to. So how would it be integrated into auditing? Well, one day the intelligence systems will be able to continuously audit a company because it will know all the rules, it'll know all the correct actions, it'll know how to notify the correct parties. Currently, it's just used to add applications, right? So it's currently used in a way where it aids auditors with the tasks that they're doing on themselves. It's still on the auditor to really decide what they want to use it for. So it's on an application type basis. And it's being used to do this, like, more efficiently and accurately so that the auditor can focus on more subjective tasks and more higher level kind of tasks that a machine might not necessarily be able to do, right? So auditors are going to have to learn how to adapt to this. You guys are lucky if any of you go into auditing, you're learning about these things in this class. Not everyone has the benefit of doing that, right? Someday this is going to be a thing that's in everyday life and everyone's going to have to learn. And you don't want to be like my grandfather, totally unable to operate a smartphone. You want to prepare yourself that when smartphones are out there, you're able to use that technology as best as you can. It provides you with job security, it provides you with the ability to function in life, right? Because if this is something that's in every home, then you're going to have to learn how to use that, all right? Even if you don't have it in your home, you might have it in a friend's house or something like that. You need to know that, hey, you might be getting recorded or something like that. These are important things to know. And then the final point here is that special consideration needs to be given to the potential pitfalls, right? I think that auditors are very lucky, right? It's usually a huge curse on auditing that for external auditors are very slow to adopt these kinds of technology. But personally, in this case, I think that it's actually good, right? I think it's good that they're implementing it on internal audit. I think this is something where the future is. It's definitely something that people need to learn and something that people need to take into account. But you need to be slow about it because we don't understand all the potential problems that could go wrong with the system, and you want to mitigate those problems as much as possible, because if they get out of control, then the next thing you know, you're Arthur Anderson and Enron's going under, and no longer are there the big five, there's only the big four, okay? And you don't want that to be your company, and you don't want to be the one that's sitting up there potentially going to jail for some sort of problem that you didn't even think would be a problem. All right? These are some final concluding remarks. Basically, they're here to stay whether you like it or not. I mean, they're in every single iPhone now. I had to update my laptop stuff, and so I have Siri now, even though I didn't really want Siri. They're being developed, and they're certainly not at the mature stage of operation, right? Like, you use Siri, and obviously Siri still has problems understanding you. They're still coming up with this idea that I talked about with the mature machine universal language to translate between languages more effectively. So it's still coming about. I mean, it's not as if you see Arnold Schwarzenegger busting the door down Terminator style yet. But we're getting there. I mean, it's on the way. The applications are pretty much endless. Like what I was saying, you could be cooking in your kitchen and you can change the temperature and you can have the system even tell you when you're missing an ingredient. There's a lot of concerns that haven't even been addressed. I'm sure there's plenty more that I haven't even thought of that aren't even in this presentation that could turn into huge major problems, right? And then the effect of these systems, right, they can be way greater than we understand because, for instance, like when people first invented the cell phone with the MP3 player, like, yeah, okay, they thought people would use it, but they didn't think that it would have the impact on social interactions that it had. Or when Mark Zuckerberg invented Facebook, or the guy, I don't even know who it was, that did MySpace before that, like, they thought they were going to bring people closer together. They didn't think that it was going to cut down on people like going and hanging out at the park outside or meeting each other up to go to a movie, right? They thought that it would help facilitate that, when in actual fact the research indicates that people feel like they get enough social interaction from that and they're not really willing to do that. So these things are going to be like very, very impactful on everything in society, and auditing is just one area of application that can be revolutionized by using this technology, right? So even if you guys go out there into the accounting world and you don't do auditing and you want to do something else in accounting, well, it's coming. It's coming to tax, it's coming to financial reporting, which is kind of auditing anyway. It's coming to management, cost accounting. Like, yeah, we invent these systems like ERP systems and all that to make our lives easier, and this is just the next evolution for that. Are there any questions on artificial intelligence? All right, enjoy the rest of your day, guys.